Jai Hind one and all. Now, in continuous with the lecture series, engineering physics, my next topic is electromagnetic theory. So this is our second unit in engineering physics, and this is called electromagnetic theory. So what is electromagnetic theory? That means it is comprises of two words. One is electro and one is magnetic. That means we are talking about electric field. Plus we are talking about magnetic field. So initially electricity and magnetism were studied separately, but in 1980 Oersted showed that electromagnet can be produced by electric current, and later the Faraday invented phenomena of electromagnetic induction, which is very famous. Phi is equal to d phi by dt. We have learned it in the previous classes also, that EMF can be induced by changing in flux with change in time. So this is our electromagnetic field. So before going in a deep into electromagnetic field, we'll study a simple definitions, and these are point charge. What is point charge? So we all know that charge can be written as Q. The charge can be written as Q, and when whole charge is centered at a point, we have an arbitrary body, and we consider that the whole charge of the body is centered at one particular point, and that is called point charge. So this is very important theory, as we have learned about point mass also. So this is somewhat same like a point mass, and we call it point charge. When we consider that the whole charge of a body is centered at a particular point, then we can say that it is a point mass. Discrete charge distribution, as name suggests, discrete. Discrete means not continuous, but after some it is having some discrete values. It has some discrete value. This is a continuous value. But if I sampled it like this, then I can say this is a discrete body. So discrete charge distribution. What is it? The system of point charges separated by a finite distance. In the previous one, what we have? We have an arbitrary body, and we say that the whole charge of a body is centered at a point, but in the discrete charge distribution we can say that they have a certain distance between them. In the previous one, in a point charge, we don't have a distance between the point. Charges are combined together. Now in the second one, as you can see, there is a finite distance between all the charges. So you can see from here, there is a finite distance between the charges, and this can be any arbitrary body. So if there is a finite distance between charges, then we call it a discrete charge distribution. We can say my Q1 is here, my Q2 is here, my Q3 is here, and they have a certain distance between them. So we call it discrete charge distribution. Now, another famous point is continuous charge distribution. Okay, continuous charge distribution. The system of charge in which distance between two successive point charges is zero. Point charges. That means that body whose whole charge is centered at a point is called a point charge. This is called point charge. And the system of charge in which distance between two successive point charges is zero is called continuous charge distribution. Now, previously you can see from here, that means all the charges are so closely packed, all the charges are so closely packed that there is no certain distance between these two. We can't find any distance between these two. So here the charge is so compactly connected to each other that there is no certain distance between them. And if there is no certain distance between them, then we can say that this is my continuous charge distribution. And continuous charge distribution can be applied or can be defined in three ways. First, linear charge distribution, surface charge distribution, and the third one is volume charge distribution. We have heard about them in 12th class, and I'll take one by one, and you will understand why we are using it, and you will recall them that we have used them somewhere, sometime. So the first one is linear charge distribution. Linear charge distribution. Take a rod and put a charge plus over it. So what will you get? And what will you understand from it? You will understand that that charge will distribute all over this metal rod. It will not stay over here from where we have put in, but it will move over here and there, and it will equally distributed with the equal distance with it. So suppose we have a charge, we have a rod, and why we are calling it linear? Because it is moving in a linear body. So suppose we have a length of a rod, length of a rod is L, and we induce a plus. We induce a positive charge in it. So what will happen? Can we get all the charge over here? We'll get nothing here. But actually what will happen, that this charge will move all over the body, and they will attain a certain distance like this. Why they are taking this? Why? And the big question why is answered like this charge repel this one, and it will attain a position, and likewise this charge is repelled by this and repelled by this, it will also get this position. So one by one after the other, all the charges will get a certain distance, and they will place equally at equal distance in a rod. So linear charge density. In a continuous line charge distribution, charge per unit length. Charge. This is nothing but a charge per unit length. The charge per unit length is known as linear charge density, and this is denoted by lambda. This is always denoted by lambda. So its definition itself explains its working, and its formula will be lambda is equal to charge per unit length, and how much charge we have? Charge is Q, and how much length we have? L. So we can say my lambda will be equal to Q by L. So again, unit. So what will be the unit? It is very easy to understand. What is the unit of Q? It is coulomb. And what is the unit of length? It's meter. So we can say that unit will be nothing but coulomb per meter. Coulomb per meter. So this is my linear charge density. Now, if we talk about surface charge density, surface. We are talking about surface, not internal, but it is a solid body with some space in it. So suppose we have body, and we induce some charge in it. We induce some charge. We can induce plus minus anything, but I am explaining it with the plus sign. So if we induce some charge in it, what will happen? The same process will happen what will happen in a rod, that it will equally distributed all over, but here it will equally distributed. Okay, it will get equally distributed on its surface. It will equally distributed on its surface, and what we'll get is, we'll get like this. So hold my charge will get distributed all over the surface, and we can say that surface is as. So again we have the formula, that is, in continuous surface charge density or distribution, the charge per unit surface area is known as surface charge density, and it is denoted by sigma. So this is nothing but sigma is equal to Q by S, and the unit again, this is coulomb and this is meter square L into B. So its final unit will be coulomb per meter square. So this is coulomb by meter, and it is having coulomb per meter square. Again, the third one, as name suggests, volume charge density. Volume charge density. Now we are not talking about a rod, we are not talking about a surface. Now we are talking about a volume. Just like a bucket we have, and we say that it's a 6 liter bucket. So 6 liter means it can have a 6 liter of water in it. So we are talking about something within the body. Okay. So suppose we'll take this example again. We'll take one arbitrary surface and we will induce plus Q charge again over here, and the volume of this is V. So we can, what will get is, it will get distributed all over. It will get distributed all over. I think you are understanding it. Okay, now you can understand the same phenomena will happen. It is a continuous volume charge distribution, and the charge per unit volume is known as your volume charge density, and we call it, we denote it with a rho, and rho is nothing but what charge we have is Q, and what volume we have is V. So again we got a formula as Q by V. Again, if you talk about the unit, this is the unit of C, and this is the unit of meter cube, L into B into S. So the unit, the final unit will come out to be coulomb per meter cube. So this is very important phenomena, and we will use them somewhere or other in next slides. Now this is something very important. We are talking about del operator. Del operator. What is del operator? We call it del operator. This is del. So we want to explain all our things in 3 directions. X, Y, and Z. Okay, we can have a coordinate system also. So we are talking about electromagnetic. So electromagnetic is nothing, is something which are perpendicular to each other, and they propagate in a third. So thirdly, what is that? If my electric field is moving here and my magnetic field is moving, then they will propagate in another one. So how to explain these phenomena, and for that purpose what we will get is del operator. So we call it curly by curly partial differentiation, we can call it. So del is equal to curly by curly I operator plus curly by curly y j cap and curly by curly z k cap. That means this is showing the value of x-axis, this is something on y-axis, and this is something on a z-axis. So this is my del operator, and this is a vector quantity. This is very important. We have to learn this only. We have to learn that del is curly by curly x I cap plus curly by curly y j cap plus curly by curly z k cap. We need to understand this thing. We are not explaining it in more detail. So we have to learn that my del operator is having a value of this. We will use them in next classes. So now the next component or operator is our Laplacian operator. And what is Laplacian? It is nothing but it is del dot del is equal to del square. And why we are getting value of this? Why we are getting value of this? If you multiply this again with itself, what will happen? As we understand from the knowledge of our dot product, and that is in dot product in dot operator my I cap dot I cap j cap k cap is equal to 1, but my I dot j, my j dot k, my k dot I all are 0. Okay, so you can understand if you multiply del I with del j with del z, then these value get 0, and what you will get is del by del x I cap into del by del x I cap plus del by del y j cap into del by del y j cap, and again so on. So what we will get is I into I is nothing but 1, j into j is nothing but into 1. So what we will get is del square by del x square plus del square upon del y square plus del square upon del z square. So this is my final value over here. This is my final value of Laplacian. Laplacian operator is a scalar quantity. Why? Here you can look I, j and k cap, which provides the value direction are present over here. I, j and k, they will provide the direction of something. So this is a vector quantity, and here we don't have any I, j or k cap, or that means we are not having only a magnitude value, and we can call it Laplacian operator. And same way we have a gradient of phi. Gradient is nothing but if something is divided by L, we call it a gradient. So that is del into phi, and divergence is called del into A, and curl. These two are very important. If we take a dot product of a del operator with some vector, we call it divergence, and if we'll take a cross product of that particular del operator with any of the vector, then it will come out to be a curl. So this will show a dot product. And this will show a cross product. So this is very important. And on these two operator, on divergence of A and curl of A, we have two theorems. And what are they? These are very important theorems. And these are called Gauss divergence theorem and Stokes theorem. Its name suggests Gauss divergence theorem. I said that if you take a dot product of a del operator with a vector, then it will be a divergence. And if you will take a cross product that particular del operator with any of the vector, then it will be a cross product and we call it a curl. So on divergence we have a Gauss divergence theorem. We have learned about the Gauss theorem in early days also in 12th, where we call in cross integral, in closed integral E dot ds. I will show you. Sorry. In closed integral, we will recall it E dot ds is equal to q upon epsilon naught. I hope you remember it. Now, so on the same phenomena we have Gauss divergence theorem. On the same phenomena we have a Gauss divergence theorem.